Section 4 involves factoring quadratic expressions. And the quadratic expressions that we're going to be working with are like trinomials. So first I want to remember what we have to do when we're supposed to FOIL these binomials. FOIL means multiply them together. FOIL is just an acronym. It doesn't really mean anything. So when I say FOIL, what are we supposed to do? So you multiply the first two terms together and you get x squared. Then multiply the outside terms together and you get 5x, so plus 5x. Then the inside terms and you get 2x, so plus 2x. And finally, the last terms, 2 times 5 is 10, so plus 10. And then what do? Combine like terms, and we wind up with x squared plus 7x plus 10. That's the answer. Now, the question is, take a look at the answer that we got. What can we say about the numbers in our answers? Where did those come from? How did we get this 7 and this 10 from our original problem? What about the 2 and the 5? Yeah, to get this one right here, 2 plus 5 is 7. To get this one right here, 2 times 5 is 10. And that pattern repeats itself when you're trying to go backwards. So if I gave you this problem right here and I said factor it, which means go backwards from the distributive property, by the way. Distributive property is multiplication. Factoring is actually division. If I said factor this, then you'd be splitting this into a FOIL problem, and you'd be looking for two numbers that add to give that. And then two numbers multiply to give that. And they're the exact same numbers. So we are going to be looking for two numbers that multiply to give me that number right there. And at the same time, those same two numbers add to give me that number right there. If I can find two numbers that do that, then I can split this original trinomial into two binomials being multiplied together. In other words, I can undo FOIL. And that's the goal of this entire section. So the official thing that we have to say is when we factor a quadratic trinomial of the form x squared plus bx plus c, what's missing here? The a, actually it's not missing, a is 1. As long as there's a 1 in front of the x squared term, as long as a is 1, then we have x squared plus bx plus c. If that's the case, then we can split this into a FOIL problem by looking for two numbers that multiply to give c. And at the same time, those same two numbers add to give b. For time's sake, we're skipping these two problems. We want to factor these two trinomials. So first of all, can I factor it using splitting up FOIL? Yeah, because the a here is 1. So that means that I can rewrite this like this. If this thing factors, it will look like that. It will look like a FOIL problem. Now on a FOIL problem, we'll have our variable here and here. So it's x and x. And now I'm just looking for two numbers that multiply to give me 24 and add to give me 14. What are those two numbers? 2 and 12. That's a positive 2 and a positive 12. And that's the answer. Check. Always check. Especially on these problems, it takes 4 seconds. Two numbers that multiply, so 2 times 12 is 24. 2 plus 12 is 14. So I know I got it right. All right? It's very easy to check these problems. The second one, can I factor this? Yep, so I can split this. Because the a is 1 here, I can do exactly what I just did. I'm going to write x and x. And then I'm looking for two numbers that multiply to give me 32, but add to give me 12. 8 and 4. Write them down. Doesn't matter what order they're written in as long as they're in there correctly. 4 times 8 is 32. 4 plus 8 is 12. So this is the correct answer. Both of those examples that we just did, and actually the other two that we crossed off, which you're more than welcome to do on your own if you want extra practice, dealt with positives. There were no negatives involved. There's always going to be negatives involved on these problems, so we need to talk about what happens when we see negative signs. There are patterns, and if you know the patterns, you can do these problems very quickly. When both signs in the trinomial are positive, both factors will have a positive in them, as we just saw. But when there are negative signs involved, things change. So there's only three other ways that this can occur if I don't see plus plus. I can see plus minus, I can see minus plus, or I can see minus minus. So if I have x squared plus the middle term minus the last term, then that means that my two numbers, in order for me to have two numbers that multiply to give me a negative, those two numbers must be what? One has to be positive, one has to be negative. So one is positive, one is negative. Now in addition to that, if I have two numbers that are multiplying to give me this negative right here, they're going to have to add to give me a plus right here. I have to wind up with a positive when I add them. So we can say one more thing about these two numbers. Yeah. So obviously with one being negative and one positive, one's bigger than the other. But the magnitude of the positive one is bigger than the magnitude of the smaller one, or of the negative one, okay? So I can say that. The greater number is positive. By greater, I mean the magnitude of the positive number is bigger than the magnitude of the smaller number. So now that I know that, and because A is 1 right here, I can split this into a FOIL problem. Again, the x and the x will go in here. But I know my signs, they need to be one is positive, one is negative. So plus, minus. And now I know that I'm looking for two numbers that multiply to give me negative 48, add to give me positive 8, and the bigger number has to be the positive one. So give me two numbers that do that. 12 and negative 4. So I'm going to write that down. That's positive 12 and negative 4. And then I'm going to check it. And again, it takes like 4 seconds. 12 times negative 4 is negative 48. 12 plus negative 4 is positive 8. So that must be the right answer. The second case, if the last term is positive, but the front term here, the middle term, is negative, what does that mean for our factors? They both must be negative, yeah. So we're both going to have two negative numbers. So I'm going to say my two numbers must both be negative. Both be negative. Nice. Why? Yeah, I got to multiply my two numbers together to get a positive. The only way that can happen is if both are positive or if both are negative. Well, there's no way I can add two numbers together that are both positive and get a negative result. So therefore, both numbers must be negative. Now that I know that, I can split this into two, making my FOIL problem. I have x and x, and I know that both of these have to be negative, so I can put those signs in there. Now I'm just looking for two numbers that multiply to give me 72 and add to give me negative 17. What are they? Negative 8 and negative 9. Write them down, check them. Negative 8 times negative 9 is positive 72. Add these two together and you do get negative 17, so you're the right answer. The only other possible scenario is if we have two negatives. So the middle term is negative, the last term is negative. In this case, we're still going to have our two numbers. The only way I can multiply two numbers together and get a negative result is if one's negative and one's positive. So I'm going to write one is positive, one is negative. Looks like lists. Maybe I should write the word one instead. What else do I know? The greater number in this case is negative. So I'll write that. Greater number is negative. So now that I know all of those things, I can break this into a FOIL problem. I'll have x and x. I'll have one is positive, one is negative, so plus and minus. And now I just need two numbers that multiply to give me negative 35, and at the same time add to give me negative 2. So 5 and 7 works, but which one's which? Positive 5 and negative 7. Check them to make sure. This is negative 35 when I multiply them. This is negative 2 when I add them. So that's the correct answer. We're skipping those bottom 5 problems. The top one, top left. Can I factor this like we have been factoring? Yes. So I can split this. If it factors, it'll look like that. I can write x and x, and then I can put my signs in there. My signs have to be both of them. They both have to be negative because they're going to multiply to give me a positive, but add to give me a negative. Two numbers that multiply to give me positive 16, but add to give me negative 10. So negative 2, negative 8. Does it matter which order you write those? No. Check them. Negative 2 times negative 8 is positive 16. Negative 2 plus negative 8 is negative 10, so that's the correct answer. Middle one. Does this factor like I've been doing? Yes, so we can do this. We can put x and x, and my signs will be one's positive, one's negative. Two numbers that multiply give me negative 12, but add to give me positive 1. Just start thinking of numbers that multiply to give you 12. 1 times 12. 3 and 4. There you go. Which one's positive? The 4 has to be positive. The 3 is negative. Check it to make sure. 4 times negative 3 is negative 12. 4 plus negative 3 is positive 1, so that's correct. How about the third one? Does this one factor like we've been doing? Why does it factor like we've been doing? Because A is 1, okay? With this format, we can factor it like this. X and x. My signs will be one's positive, one's negative. Good. Two numbers that multiply to give me negative 18, but add to give me negative 7. Two and 9 works, but it's a negative 7 here, so the 9 must go there and the 2 must go there. Check to make sure that you're right. 2 times negative 9 is negative 18. 2 plus negative 9 is negative 7, so this is the correct answer. Always check. So many times there's a couple numbers that seem like they work, but they don't. Once you write them down, you can see that. How about the middle one? Can we factor this one like we've been doing? We can? Okay. So what are we looking for? Two numbers that multiply give me 21. So this is written in the wrong order. You can and you should probably rewrite this so that it's in the correct order. It's the x squared term or the squared term first, so that's m squared. The linear term or the first degree term second, so that's minus 22m. And then the c term, the constant term, plus 21 last. That really helps a lot because it's easy to get confused. Make sure that it's in the correct order. Now this can be factored. I have m and m. My two signs are going to be both negative. Two numbers that multiply give me positive 21, but I get to be negative 22. Good. Don't forget about the ones. 1 and 21. A lot of people will forget those factors. Negative 1 times negative 21 is positive 21. And if I add those two numbers together, I do get negative 22. So this is the correct answer here. Okay, we're skipping those two problems, and this is an important concept right here. Anytime you're doing a factoring problem, your first step, the first thing you need to do is look for a GCF. GCF means greatest common factor. You find the GCF. If it's something other than 1, you factor it out, and then you write what's left over. And then you continue factoring if there's more factoring to do. And you will continue factoring until all of the factoring is done. Okay? Now, on this problem, is there a GCF? To do a GCF, look at the numbers. 6 and 9. The greatest common factor between 6 and 9 is 3. But you also have to look at the letters. N squared and n, there's a GCF there as well. It's n. So 3n is the GCF. Open up parentheses and now tell me what's left over. 2n. Plus 3. Close your parentheses. Remember, factoring is like dividing. If I divide 6n squared by 3n, I get 2n. If I distribute this back in just to check, I have 3 times 2, which is 6, n times n, which is n squared, and then 3n times 3 is plus 9n, which is exactly what I started with. Okay, how about the second one there? We have a GCF of 4. So I would write the 4, open up parentheses, and what's left over? $14. Okay, so we factor the GCF out. Now, in this problem, there was no more factoring to do. Is there more factoring to do in this problem? Potentially, yes. So if there is, we need two numbers that multiply to give me what? Negative 14, and add to give me what? 5. Are there two numbers that do that? What? There you go. So this actually does factor. We have 4. This is going to break then into my FOIL problem. I'll have x and x. My two signs must be, one's positive, one's negative. And now I need two numbers that multiply to give me negative 14 and add to give me positive 5. 7 and 2. 7 has to be the bigger number. 7 is the bigger number, so it has to be the positive one. And then the negative 2 is the little one. Check to make sure. 7 times negative 2 is negative 14. Add them and you get positive 5. So this is the final answer. You have to continue factoring until it's all done. How about this one with the 9s and the 18? GCF is 9. We're not dividing, we're factoring. And I'm left with plus x minus 2. Okay. Does the thing inside factor more? If it does, then we'll wind up like this. A 9 out front still, and then break this into a FOIL problem. X and x, my two signs would have to be, one's positive, one's negative. And now we're looking for two numbers that multiply to give me 2, but add to give me negative 2, but add to give me positive 1. There's only two numbers that multiply to give me 2. What are they? Yeah, 2 and 1. One has to be positive, one has to be negative. Check to make sure. 2 times negative 1 is negative 2. 2 plus negative 1 is 1. So this actually did factor. That's the answer. Include the GCF in your answer. How about this last one? What do we do? If I distributed, then what would I have to do? Factor. And what would I factor out? That. So how about we put our shoes on and tie them and then untie them? Or we just realize that that is already factored. There's nothing to do there. Here is the mother of all factoring right here. When we're presented with x squared plus bx plus c, when a is 1, we can do what we've been doing. But when we have an a, in other words, when a is not equal to 1, when there's a number in front of a, then you're going to have to do this process here. It's a lot of words, but it really boils down to just a few steps. It's basically just a routine that you follow. And once you follow that routine, then you will be able to factor this fairly easily. So the first thing that you do when you're presented with an expression that looks like that is you look for a GCF. That's still step one. Step one, look for a GCF to factor out first. Always do that. If there is a GCF that you can factor out, it could be that the A will get factored out completely. And if that happens, then you're left with just an x squared plus bx plus c inside the parentheses, and then you don't have to do this method anymore. A lot of times, though, you will still have an A, so you will have to use this method. So, just as an example as we go through this, let's use 3x squared minus 17x plus 20. Okay, in this one, there is no GCF other than 1. So so we move on to step 2. We got to multiply A times C. Well, A is this guy, C is this guy. So I'm going to write down AC equals 60. That's step 2. Step 3, find two numbers that multiply to give me that number, but add to give me that number. So I need two numbers that multiply to give me a positive 60 and add to give me a negative 17. That means both numbers have to be negative. So I need two numbers that will do this. Negative 3 and negative 20 do multiply to give me 60, but they don't add correctly. Negative 5 and negative 12 does work. Negative 12, negative 5. Write them down and then check. These two multiply to give me positive 60. They do add to give me negative 17. There will never be more than one correct way to do this. So these are the only two numbers that work. That's step 3. Then step 4 is set up the box. The box looks like this. This is called the box method. Actually, it's called the area method, but I call it the box method because that's like 2 less syllables. Okay, so we've set up the box. Now, part A, place the first term, the x squared term, in the first box. So that's going to go right there. Place the last term, the constant term, in the last box. So this guy goes right there. The constant term, not the AC, the constant term. Then part C, place the two numbers from step 3 into the other two boxes and attach the variable to them. So we're taking this negative 12 and this negative 5. We're tacking the variable onto them, and that negative 12 is going to go there, and that negative 5 is going to go there. So I have negative 12x, negative 5x. From the x squared term going in the first box, I'll have 3x squared there. And the constant term going in the last box, that 20, will go there. That sets up the box. And that is all of step 4. Now step 5 says factor out the GCF in each row and each column in the box. So what you're going to do is you're going to look at this top row, figure out what the GCF is, and write that GCF right there. Same thing in that bottom row. Write the GCF right there. In that first column, find the GCF of these two boxes and write that answer right there. And in the last column, find the GCF of these two boxes and write that answer right there. So in the end, you'll have a GCF for that first row, a GCF for that second row, a GCF for that first column, a GCF for the second column. That's step 5. But the important thing right here is this. If the first box in the row that you're factoring a GCF out of, or the first box in the column that you're factoring the GCF out of is negative, then the factor that you pull out will also be negative. So, in this row right here, that first box is negative, so the factor that we pull out would be negative. In this row, the first box is positive, so the factor we pull out will be positive. In this first column, the first box is positive, so the factor we pull out will be positive. In this one, the first box is negative, so the factor we pull out will be negative. Finally, in part B, number 5b, the terms across the top and the terms across the side are your factors. So you'll be able to take those factors and write them like a FOIL problem. If you have a GCF from the beginning, then that GCF will be included right here in the front. And that's it, okay? The more you do problems like this, the faster you'll become, to the point where you could probably solve one of these problems in about 15, 20 seconds. Okay, so let's practice using the box method. First of all, on this problem, what do we do first? Look for a GCF. Is there one here other than 1? No, so the next thing we do is what? AC, write down AC equals what? 6. So now we need two numbers that multiply to give me 6, but add to give me B, 5. What two numbers do that? 2 and 3. Check to make sure. 2 times 3 is 6. 2 plus 3 is 5. So I do have the correct two numbers. Now we can set up the box. What goes in this first box? The 2x squared. The first term goes in the first box. What goes in the last box? The 3. The last term goes in the last box. How do I make these two boxes? Tack x onto these two numbers that I picked and put them in the box. It doesn't matter which way they go. So I'll put the 2x here and I'll put the 3x here. So now the box is all set up. What do I do now? Factor the GCF for each row and each column. So for this top row, what's the GCF? X. 1 for the 2 and the 3, and x for the variables. And the GCF in the bottom row is 1. There will always be a GCF that you write down. If there is no GCF from these numbers, then the answer is 1. How about the first column? 2x, and the last column, 3. So now the factors are sitting right here. Here's one of them. Here's the other one. So I can write 2x, that's a positive 3, so I write plus 3, times x, that's a positive 1, so I write plus 1. That is the answer. Second problem, what do we do first? GCF is 1. Okay, now what? AC is 30. So I need two numbers that multiply to give me 30, but add to give me negative 13. How is that possible? Both numbers have to be negative, which means that they have to be negative 10 and negative 3. That's right. Check to make sure. Multiply them together and you do get positive 30. Add them together, you do get negative 13, so we're good to go. What do we do now? Set up the box. What goes here? 5x squared. What else do I know? 6 in the last box. Now what? Negative 10x here maybe. Negative 3x there. Now what? GCF for each row and each column. So for the top row, the GCF is x. For the bottom row, the GCF is, it is negative because that first box is negative. And then for 10 and 6, the GCF is 2, so negative 2. First column, GCF is 5x. Second column, the GCF is negative 3. It's negative because the first box is negative. It's 3 because the GCF of 3 and 6 is 3. Now what? So write your factors and you're done. We have across the top 5x minus 3. Across the side, x minus 2. There's your answer. For the third problem, what do we need to do here? GCF, actually there is one this time. What is it? 2. So we factor out the 2 and we write what's left over. What's left over? 3x squared 11x minus 4. Okay, now we need to check to see if the thing inside factors as well. So we factor out the GCF. What happens now? What happened before? We have a problem that looks like this. Looks a lot like this problem. We need AC. AC is what? Negative 12. So we need two numbers that multiply to give us negative 12 and at the same time add to give us positive 11. What are those two numbers? 12 and negative 1. Write down those numbers and then check. 12 times negative 1 is negative 12. 12 plus negative 1 is 11. So we have the correct two numbers. Set up the box. What do we know? What? 3x squared. We factored out the GCF and now we're ignoring it. We are going to include it in our final answer, but we do not include it when we're writing our box. So it's 3x squared. What else do we know? Negative 4. And what else do I know? 12x, negative 1x, or just negative x. And again, those two boxes can go in either order. It's a lot of purple. Okay, what do we do now? GCF for my first row is x. For my bottom row, it's 4. For my first column, it's 3x. And for my second column, it's -1. So then my answer is going to be 3x minus 1 times x plus 4. Don't forget about your GCF hanging out up there. You have to include the 2. So it's actually 2 times 3x minus 1 times x plus 4. We have 2 more things to talk about in this section. The first one is perfect square trinomials. Now, perfect square trinomials are a pattern. There's a lot of patterns in algebra too. There's actually a lot of patterns in algebra as well, just all over the place. There's patterns. This is one of them. You don't have to know it to still be able to solve the problem, but it does help sometimes. If the pattern is there, then you can factor it using the shortcut. If the pattern is not there, you cannot force the pattern onto something that is not a perfect square trinomial. You'll instantly get the problem wrong. So you have to check to see if the pattern is there first. If it is, you can use it. If it's not, then you can't. If you don't remember the pattern, then don't bother trying to think about it. Just factor it the way we have been factoring. So first we want to FOIL both of these. What do I get when I FOIL a plus b squared? That's what everybody always says, but you didn't FOIL. You tried to distribute the exponent, and that does not work. You can never distribute exponents. Exponents mean the thing is being multiplied times itself. So we have a plus b times a plus b. And now we FOIL. So that would become a times a, which is a squared. A times b is positive ab. B times a is positive ab. And then b times b is b squared. So now we combine like terms and we get a squared plus 2ab plus b squared. Don't distribute exponents. For the second one, it's the same idea. It's just that we have a minus sign sitting there. So instead of writing the square, I'm going to write a minus b again, and then I'm going to FOIL this. A times a is a squared. A times negative b is negative ab. Negative b times a is negative ab. And then negative b times negative b is positive b squared. Combine like terms and you get a squared minus 2ab plus b squared. Because we used only letters, we have proven that to go from the original problem here to here, all we have to do is square the a, square the b, then multiply these two numbers together and double it. Here all we have to do is square the a, square the b, then multiply these two numbers together and double it. What is the only difference between these two? The negative sign. On this one, this term is positive. On this one, the middle term is negative. Where did the negative sign come from? Right here. These are patterns that you can use. If I want to go this way, I can use that pattern. But if I want to go backwards, if I'm giving you this problem here, and you want to factor it, if it shows this behavior right here, you can reverse this and go back to this. This is a perfect square trinomial, and so is this. Note the sign here, note the sign here. Okay? That's what this paragraph right here is saying. To recognize the pattern, first, look at the first and last terms. Are they perfect squares? If they are, you could be looking at a perfect square trinomial. To figure out if you are, take the square root of each a and b. What's the square root of a squared? What's the square root of b squared? B. Then multiply those two together. If I multiply a times b, I get ab. Then double it. By doubling it, that gives me that middle term. If I get exactly what the middle term is, if I take the square root of both of the end terms, multiply them together, then double it. If I get that middle term, then I'm looking at a perfect square trinomial, and I can instantly go to this using the pattern. If the pattern is not there, or if you don't remember the pattern, then you need to do it the long way, using just factoring. So the steps are here. Let's see if this is a perfect square trinomial. Let's see if we can use the pattern, okay? Is this first one a perfect square? Yes. Is the last one a perfect square? Yes. So we could have a perfect square trinomial here. Doesn't mean we have one, it means we could have one. We have to check the rest of the pattern. So what's the square root of a squared? It's a. What's the square root of 36? It's 6. Multiply those two together and you get 6a. Now double it. Do we get the middle term? Yes, we do. We get 12a. What about the negative? The negative shows up here. And then we're going to factor it into that. Okay? So the pattern is there. The negative sign tells me that I'm going to have this setup with a negative sign in between. The pattern is there. This term is the square root of that first term, a. This term is the square root of this term, 6. That's your answer. So when you're dealing with a perfect square trinomial, if you can recognize the pattern, the work is non-existent. You just have to write down the pattern. If you don't recognize the perfect square trinomial, or if it's not a perfect square trinomial, then you use the long way. You could factor this problem and wind up with this. Just takes a little bit longer. How about the second one? Is a squared a perfect square? Is 25 a perfect square? So is this a perfect square trinomial? We don't know for sure. We have to finish the pattern. So the square root of a squared is a. The square root of 25 is 5. Put them together and you get 5a. Double it and you get, is that the middle term? Yes, we do get the middle term here. So this is a perfect square trinomial. I can write it like one. The sign in between will be plus because of that plus right there. Plus, and then my first term will be a. My last term will be 5. The last one, is this a perfect square trinomial? No, this is not a perfect square. N squared is, but 6 is not. So therefore this is not. And even if this was, 8 is not a perfect square either. So this is not a perfect square trinomial. So what could I do? You still got to factor it. The directions say factor it, so I got to factor it. If it factors. If it's going to factor, I'm going to have to factor out a GCF. Is there one here? 6, 19, and 8? No. So that means I'm using the box method, and I'm just going to rip through the box method here. I have AC equals 48. I need two numbers that multiply to give me 48, but add to give me 19. The two numbers that do that are the ones that everybody always forgets. 16 times 3. 16 times 3 is 48. 16 plus 3 is 19. So I can set up the box. First box, first term, 6n squared. Last box, last term, 8. The two numbers that I just picked, 6n and 3n. For my top row, GCF is 3n. Bottom row, GCF is 8. First column, GCF is 2n. Last column, GCF is 1. So my answer is 2n plus 1 times 3n plus 8. I couldn't use the shortcut. It was not a perfect square trinomial. The world did not end, though. I can still factor it using the box method, and you just saw how quickly you can do the box method with practice. The last pattern that we're talking about in this section is this guy. If I have x plus a times x minus a, we get x squared minus a squared. This is called the difference of squares. The reason why this happens is if I FOIL this out, I get x squared. But then I get minus ax, and then plus ax, and then minus a squared. What happens? The ax's disappear. The o and the I that I calculated out drop out. This situation actually has a special name. They're called conjugates. We're going to be working with conjugates a lot for the rest of this chapter, so it's important that you know them well now. This pattern right here turns into this right here. To go this way, all I have to do is square the x and square the a and put a minus sign in between. If I have the difference of squares, I can go the other way very quickly. The square root of x goes here and here. The square root of this guy goes here and here. And then I put a plus and a minus in between them, and I'm done. So this is called the difference of squares. When you see two terms that are perfect squares and you are subtracting them, you can factor them instantly. This one is incredibly powerful. Again, if you don't remember the shortcut, you can still come up with the right answer in the end. But this one is so important that you really need to know this one well. So take a look. Is 25x squared a perfect square? Yeah, because 25 is a perfect square, and so is x squared. Therefore, the whole thing is a perfect square. Is 49 a perfect square? Yes. Are we subtracting those two perfect squares? Yes. And because we are, we can break this into this situation. So now we just take the square root of each of those terms and put them in the same spot down below. So the square root of 25x squared is 5x. The square root of 49 is 7. And I just repeat that over here. That's the answer. How about the last one, 16x squared? Is that a perfect square? Yes. Is 81 a perfect square? Yes. Are we subtracting them? Yes. So this is the difference of squares, so I can factor it into conjugates. A plus and a minus. My first term will be 4x. My last term will be 9. Over here I'll have 4x and 9. Those are your answers. So we have the box method. We have factoring out of GCF. We have, I don't need the box method if A is 1. We have perfect square trinomial patterns. We have difference of square patterns. All of this in this one section. And that is the whole section.